present on environmental life cycle assessment of magnesium batteries. So please, Marcel, go ahead.
Okay.
You'll have to switch the screens, please.
Okay. Now it's working?
Yes, thank you.
Okay, perfect. Yeah, thanks a lot, ladies and gentlemen. Many thanks for the invitation for this talk, and to also have maybe a little bit a broader perspective on this issue, and coming more from an environmental perspective and doing a LCA for magnesium sulfur batteries. And actually, why are doing all these investigations towards post-lithium batteries? Yeah, because well, the present lithium-ion batteries can be considered as unsustainable. Why? Because the production costs and the life cycle costs, which include also the use phase, are still too high in many applications. The environmental impacts and the social impacts of the production are quite high, and that includes also toxicity of the materials, which is also already mentioned several times during these talks. The technical performance needs improvement, yeah, especially to decrease the costs and the environmental impacts. On that, especially focus then on the use phase, and that means we have to improve the cycle lifetime, the internal resistance, maybe the calendric lifetime, and so on. And the present recycling of lithium-ion batteries is too complex, and you need a lot of energy to get all the materials outside. And in fact, lithium, for instance, it's quite often not recycled because the costs are too high to get the lithium outside. Also, if some recycler always promise it's technical possible to get the lithium outside, but the costs are in most cases too high to get the lithium outside. And they only recycle in the moment the really expensive metals like cobalt, nickel, copper, and so on. Then also safety issues are problematic of lithium-ion batteries, especially during the use phase, but also the second use phase are more and more important. If batteries from maybe mobile application in vehicles then are used in a second life for stationary application, there are safety issues which has to be solved. And last but not least, also for the recycling, yeah, it's the safety issue big problem because of the electrolyte, which is flammable and explosive, and so that's always a challenge. Always a challenge for the recycling process. Yeah, and last but not least, yeah, the basic idea is, of course, to replace critical metals like cobalt, lithium, nickel, copper, and so on. And if you look on the criticality map of the EU, which was several years established, then you see in red, from the EU perspective, critical metals or raw materials, and in blue, the not so critical metals and raw materials. And in fact, we did some investigations regarding lithium-ion batteries and the availability of these materials in the long term. That means if we would use such materials until 2050 for really a revolution or transformation of the mobility sector, or the transformation of the energy sector, which also needs then, or there's then a high requirement of stationary storage facilities. So, and the outcome of all these investigations, and you can find the publications on our website from my group, the outcome is that really not only cobalt is critical, yeah, it's also lithium, it's also copper, it's also nickel. That means also NMC 811 is maybe not the solution to have a not critical or not to solve the criticality of the raw materials. So, and now, but the magnesium batteries, and if you look for the criticality of magnesium, now it's really above everything. So from an EU perspective, magnesium are one of the most critical raw materials, and that's really a little bit astonishing, especially, and that's also mentioned several times already. It's magnesium is the 8th most abundant element on the Earth crust. And the resources, and that's dolomite, magnesite, serpentinite, a lot of magnesium, evaporites, brines, even seawater, and then all the resources are really enormous. And so there is not really, a big shortage, and the availability should be not a big issue. But the problem is that magnesium is predominantly produced in China. So they take over the market more or less. Yeah, there's only minor production in Russia, Kazakhstan, and a little bit in US and South America. So yeah, that's the basic issue. And but on the other side, magnesium is very important for the EU, especially for alloy production. And the EU is also only depending on imports. Yeah? And also, if there's a small recycling established in the EU, but net, we are totally importers, and that makes this material so critical. And there are only small activities in the moment in the EU, in Turkey and Serbia, and of course, that's not in the moment the solution of this problem. But what happens? Why is China now leading that? Well, they really offered in the past magnesium to really low price, and it was so low that the smelters in EU was not competitive. So they shut down. The last one in Norway and France, and so until today there's no magnesium production in EU besides the small activities, as I said, in Turkey and Serbia. So the criticality, and that means that the EU perspective is not based on the availability of the magnesium, but it's rather on the high dependency from imports, especially from China. And so that means from a broader perspective, if once magnesium batteries would be successful and there's really foreseeable that magnesium, there could be a certain industrial production of that, then of course there should be then a magnesium metal production also established in EU in time. That's the point. Though be prepared for if the magnesium batteries will be successful in the future. But now coming to this, to our investigation and the investigated prototype cell. That was a cell which was produced by Custom Cells in Germany and consists of one anode, two cathodes, sulfur cathodes, and then in a pouch housing. And this prototype is, of course, not optimized. There was only the idea that there should be a cell with a function. And so the casing, that means the pouch casing, was just totally too big. The separator was double. It was a folded separator, and therefore there was also too much electrolyte in the cell. Therefore, we considered actually in our investigations 3 different scenarios for such investigation. That was the magnesium sulfur baseline scenario. That means really the prototype not optimized as it is, and then to optimize this cell and regarding the pouch mass, because the pouch mass was totally too huge, and we reduced the pouch mass from 45 weight percent to 3 weight percent. On 3 weight percent actually represents the normal weight percentage in a normal lithium-ion cell. With the next evolution, then just theoretically, that the magnesium evolution 2 Then to also reduce the separator share, that means from 10% towards 2% of the separator, and reduce the amount of the electrolyte accordingly. Those are the three scenarios which we investigated in this environmental investigation. Because the cell, from our perspective, of course, is quite important, but we need a battery. And so we consider then the magnesium battery, which consists of 80% cell in our scenario, 5.5% of battery management system, and 40.5% of casing. That's the normal numbers, average numbers, which you can find for lithium-ion battery systems. So we just use this as a comparable system. For our life cycle assessment, as I said, it's a prospective life cycle assessment because the magnesium battery is really still in the early stage of development. That means it's not a hard LCA with really hard results. So that's always there's an outcome of the results, and then maybe receive new information from the technology developers, and then we improve our LCA. So that's always a snapshot, a certain snapshot for this investigation, and the results are normally used from the technology developers to improve their systems, to make their systems more sustainable or environmental friendly. For instance, just get rid of some toxic materials. So that's the considered system for this life cycle assessment, and I will not go in detail what is a life cycle assessment, because that would be maybe too much for this presentation. So if you have questions regarding life cycle assessment, especially for energy storage, so please contact me after this session. So and you see now here the system boundaries. We have some inputs and outputs. And in general, well, the inputs are always energy and materials. That's the raw materials and energies in different forms. And the output are beside the product, the magnesium-sulfur battery, then also emissions to the different areas to water, soil, and air. And you see within the system boundaries the different components of the cell. That's the anode, the cathode, the electrolyte, and I have to say the electrolyte are still a normal electrolyte. It's not such a sophisticated electrolyte, what we already heard today with boron and so on. That would be the next step, to have also really a modern electrolyte. And then with all these components, then you have the cell assembly with all the different components. And last but not least, then for the magnesium battery, then to add the battery management system, the casing, and then to have in the end the battery of the magnesium cell. So that's the system boundaries. And with the next slide, we see already the result of this study, and as I said, there are preliminary results. And that's here we showed a really simple environmental indicator. That's the cumulative energy demand, the CED, and that counts all the different energy forms which are used for the production of the cell in this case. And that means not only the energy, for instance, electric energy, which goes in this system, but also then maybe the coal, which is used or to produce the electric energy. That means the complete pre-chain of the energy provision. And if you look for this not optimized baseline scenario that we have for this cell type, that we have a certain different contribution to the overall impact. And you can easily identify that natural gas has a certain contribution. The natural gas is used for the production of the cell, the provision of heat for the production of the cell. Then electric energy for production is the biggest contribution. The housing, that means in this case the pouch of the cell. Also electrolyte really has a big contribution, and also the magnesium itself. So, and if you compare now this scenario, this baseline scenario now with these two other scenarios, which I showed beforehand, you see that the impacts with the theoretical scenarios are significantly lower. And you can see that, very significantly that, for instance, the housing, which has a big contribution in the not optimized case, has now really a little impact, and it's more reliable, I would say. And even now with the next evolution, then with the separator, which is now adjusted to normal values, although that looks now more reasonable, and also now with the saved electrolytes. So that could be the direction of the improvement of such a cell, also if it's just on a theoretical level. Now to other impact category, it's called global warming potential, GWP. That's the CO2 impact and the equivalence also from other gases. And you see here actually more or less and very similar results. The not optimized magnesium battery cell has quite a big impact with this first optimization of the adjustment of the pouch. Now absolutely better, and now even with the improvement regarding the separator and the electrolyte, now it's really a relatively low value. And what means relatively low value? Just for the comparison, I put here now the LFP battery system. And you see, at least from the feeling, that now with this theoretical improvement of the cell, that we at least in the range of this LFP system. But I have to say, for this LFP data set, that's already quite old. That means it's from 2011. That means present LFP systems, maybe now even now the new one from BYD or Tesla, that could be significantly lower. So that would be quite interesting. But at least you see, if you improve the cell in a certain way and do it more in a to cell which are comparable to the lithium-ion battery cell, then you are in a certain way competitive, and that's already quite good. To see where in detail where the differences from the impact. So now we did also some sensitivity analysis, and though it's quite important to know where's actually the electricity production for my battery production, and of course there could be maybe coal power, for instance, like in Poland, or nuclear power or renewables, and so we try to consider that and look for the energy mix of the electricity provision for 3 different countries, which are maybe stand for a certain type of electricity mix. Switzerland with a low CO2 impact because they have a high share in hydro and renewables, and only a little share in fossils for the energy provision. In contrast, maybe then the EU in the middle, more or less, with a noteworthy fossil contribution. Then maybe China, which has still a major contribution from fossils, especially from coal power plants. So that are the 3 different countries for the potential production of the batteries. And here now you can see already then the influence of this electric energy provision. And for the EU, it's the normal that's maybe in the middle between China and Switzerland, because it has also from the CO2 emissions are in the middle. And the biggest impact from China and the lowest impact from Switzerland. And so maybe you can easily understand why companies like Tesla or Northvolt in Sweden they are so interested to have a green pre-chain for the electricity provision. That's quite important, that the impact of the cell production is really quite low and to be competitive with other technologies. So that's the reason why they're doing that. Well, in this investigation, we did not include the use phase, like cycle life, calendric life, the internal resistance, the efficiency of the cell, or power density, and so on. And that is, of course, the next step, but the uncertainties are still quite high, and there are not so much cells available, which are really full cells and are tested regarding the cycle stability or regarding internal resistance. So if you have a project, or if you have a cell in your lab, please contact us. That would be quite interesting for us to see, well, where's the range, where can be such magnesium cells perform. And another point which is not included is, of course, recycling. I say the recycling of lithium-ion batteries is quite difficult. It costs a lot of energy or chemicals. And so there should be different, for all the post-lithium batteries. And with the next graph, or maybe I can stress this a little bit. If you see now here the different value in the cells, from NMC 111, there's a lot of cobalt in it, and therefore the value is quite high. So if you recycle such a battery, then you are quite lucky, because you can get all the cobalt out of it, and also, of course, other materials like copper and nickel and manganese. But already with NMC 811, that's already not so nice from a recycling perspective, because the cobalt is only a low amount of cobalt is in such a cell. And when with LFP, there's no cobalt. And then, of course, from a recycling perspective, it's not so interesting, especially the black mass. Maybe then the aluminum is interesting and the housing, but not the black mass. And if you think about the magnesium-sulfur system, the value is even lower. And then, of course, then you have to think about how you can recycle such a system with such low value of the materials. And from our perspective, then, of course, there's no way to go a really complex recycling route. There's only the way after the use of such a battery, a stationary or mobile application, or maybe after second use, then to bring it to a mechanical treatment and then try to have a direct recycling of the cell. That, of course, would be beneficial. Otherwise, the costs for other processes are too high, and you would lose a lot of money. And that's, of course, not in the kind of cycle of circular economy. So that's maybe just some reference regarding our ongoing work. It was, the first LCA was already published for magnesium batteries in 2019 in this nice book from Max Fichtner regarding magnesium batteries. Then we had some publications regarding recycling of different battery types, and last but not least, just accepted in energy storage. The assessment of a new generation of magnesium-sulfur battery systems. That's from my side. Thank you for your kind attention. I'm looking forward for the question. Thank you.
Thank you, Marcel, for this interesting perspective on things. It's good to see that maybe there are also other aspects to consider, right? We always say, well, magnesium is so abundant, no problem, but there are other aspects which also need to be included in the picture. So I think there's at least one comment. Max, I'm handing over to you.
In fact, there is a comment from Daniel Höche that general information on primary magnesium production can be found, for example, here in Zuliani, Douglas, and Douglas Reason, making magnesium a more cost and environmentally competitive option from 2012. So
good. I look on this specific source. Thanks a lot.
Okay. I have a question, and on your slide 9, you had the energy costs.
Was not the cost.
of a watt hour, yeah, so the watt hour per watt hour.
Yeah.
So you came to a number of 1600 watt hours for 1 watt hour of a system. Can you compare that to lithium-ion battery? I mean, we had the comparison with the global warming potential, yeah, and we were at least in the range of a LFP battery from 2011, yeah. But how is it here? I mean, 1600 watt hours per watt hour.
Yeah,
this is a lot.
Yeah. Well, actually, if I delete now this one, you see with this improvement, then you are already in a nice range, between 800 and 300 or 400, I can say. Yeah, so that's already quite nice. And actually, it is. I have the slide not with me, but it's really similar to this GWP, global warming potential. It's very similar. We are in the range with this improvement, but this is only a theoretical improvement. So the technology developers, they have to show that they can produce such a cell. So therefore, I'm quite interested that maybe other groups or maybe of course also the groups with Celeste, that they develop such cells and test it, and that we have primary data, and then as if we receive more data, then of course our results are more reliable. So I'm looking forward. So that means that in the moment a theoretical improvement, and we need some confirmation from the technology side if this is really manageable. I think it's manageable, but nevertheless, there needs proof of that.
Okay. I think there will be more of these studies when we make more progress with our materials.
Yeah.
Yeah. So I think that the first pouch cells have been made already with systems that work kind of well. Yeah. Among them are organic materials, few inorganic materials. So let's see how the whole field develops.
Yeah.
So at this point, I would like to thank you. I would like to thank all the speakers today for their great contributions. We saw a lot of new results, and there were really interesting achievements in them. So how can we get better recycling? How can we boost the mobility, etc.? And I'm now looking forward to the day tomorrow, where the eMagic project, where I would say the senior scientists and the young scientists are going to present their results in 12 talks tomorrow. And this will be moderated by the coordinators of this project. So with that, I'm finished. Thank you all. I hand over to Christian.
Yeah, thank you very much, Max. I don't have much to add. Tomorrow we'll continue at 2 p.m. Central European Summer Time. Of course, all panelists are asked to join early, 20 minutes before, so that we can iron out last issues. And as Max said, Luis and Alberto from CEDETEC will host tomorrow's session, and I'm looking forward to it, and I wish you all a pleasant afternoon. Special thanks to the colleagues from Japan and China and Korea who have really stayed until now. It's now late at night, so thanks for bearing with us. And we'll see you guys tomorrow. Thank you very much.
Yeah. Bye-bye.
Bye.